Now there are legal issues in telemedicine. Suppose anything happens to a patient, who will own the responsibility? Across the countries you are doing it. Who has the license? So these legal issues, they are very important, especially when you are going cross countries. So they have to be addressed. Who will be the liable? And then of course confidentiality of the patients also is there. Then comes wireless integrated network sensors. This I was telling you, this is the real happening thing, which you will just in few years you will find that everybody will be talking of WINS, employing WINS here, there. It comes under the area of pervasive computing. Like you have heard of pervasive computing, wearable computing, pervasive computing. You are carrying computers with you in your whole body, in your clothes the computers are there. So they are monitoring you, everything. So this field of pervasive computing is there, where smart, small, smart and cheap. All the three things are very important. They have to be small, these computers have to be very small in size, they have to be smart, and they also have to be cheap, because you have to deploy them in hundreds and thousands and millions. So unless the cost is very less, you cannot even deploy them also. So this is the pervasive computer says that they will eventually pervade the whole environment, and this WSN, that wireless sensor network, this is the first real world example of pervasive computing. Now what does this mean? This, as the name says, it's wireless integrated network sensors. So it is networking, they have the wireless capability of communicating, then they are small in size, isn't it? So these WINS, they will provide sensing, local control and embedded intelligent systems in structures, materials and environments. They are combining sensing, signal processing, decision making in compact, low power. So each word has a meaning. Compactness has to be there, then low power. This I'll tell you, because low power is very, very important. You are putting them for years to, suppose you have to monitor some bridge and you have to monitor its health. So that will be, they will be embedded in the bridge for many, many years, and they have to keep working for so many years. So they have to consume very less power. They should have rechargeable batteries. They should charge themselves from the environment itself, isn't it? And the working principle of these WINS is people learn to make sense of the word by talking with other people about it. Like when we talk, we discuss, then our knowledge increases always. So there also the working principle is this only, the people talk. So they are always talking with each other. So it is a network of cooperating objects. This is a brainchild of Professor Chris of University of California, Berkeley. You have the first, this project was Smart Dust project, which was there at University of California only in Berkeley. And as I was telling, that instrumentation is always leveraging other technologies. So what technologies it is leveraging? IT, wireless sensor, wireless communication technology and sensor technology. So these are the three things it is leveraging. So the driving technologies are microelectronics, miniaturization of energy capacity. You want more and more energy in small and small size batteries. So miniaturization of energy capacity and system on chip integration technologies. So these are the three driving technologies which are behind WINS. And this MIT Enterprise Technology, they always bring reports, and they have listed wireless sensor network as one of the top 10 technologies that would effectively change this world. And because there has to be commercial incentive also, why will people go and work on this? So the market is also expected to cross $1 billion by 2009. That is the projections around the world. So as you know that internet, in 90s internet came, and it forever has transformed the way we are interacting with each other. And how we will interact with the real world outside, that will be, revolution will be brought by the sensor networks. This is how the comparison is made between internet and sensor networks. So sensor network will promise to forever transform the way we interact with the physical world. This is the architecture of sensor node. You have sensor plus ADC, you have CPU plus storage, and you have transceiver. Both way communication is there. It has to receive also, it has to transmit also. So this is the architecture of sensor node. So you can see like these are all disk, they are all sensor nodes only. Then finally you have this network bridge. Then you can go to conventional network like internet or other, then you can connect it all around the world. So this gateway is there, and then these are your nodes. Now there could be ways of communication like this. These are the nodes and this is the gateway. Now all the nodes, they are connecting to gateway. Other thing is the node, this node gives to this, is a chaining method, and this node then is connected to it. Not all nodes are connected to the gate. So there could be two configurations possible. This is called a chaining method and this is a direct method. So in first method, nodes will directly communicate with the gateway in its cluster, and the second, nodes use chaining in order to communicate with the gateway. So using chaining, what happens is that not every node is transmitting to the gateway. So it reduces the energy which is required for transmission. Otherwise all the nodes will be transmitting to the gateway only. But of course the processing will be more because every node has to receive and transmit the messages. So both plus minus points are there in both of them. The design factors and wins are, one is a fault tolerance. You have to have large number of them so that even if some of them fail, then also the network should be able to work. It should have a high level of redundancy that should be made into it. Then scalability should be there, that even some of the power supplies of some of the nodes have completely vanished. Then what you are doing is, suppose you are putting some new nodes, or even if you are not putting, then your protocol should be scalable. It should be able to do with those nodes only. So scalability and fault tolerance are important, and then of course cost is a very, very important thing. Why it has not been become popular up till now is because of cost only. You have to bring down the cost, then only it will be successful in commercial applications. Because you have to employ them in large numbers, and most of the networks, most these nodes will be disposable, because once they drain off you will dispose them off, isn't it? So having a low cost for sensor node is a must. Only when you bring down the cost per node, then only it will be successful. And MOTE is a generic name for this wireless sensor network, MOTES, that's the name. And it's sometimes called Smart Dust also, because Smart Dust was the project which was given this responsibility of making the MOTES. So Smart Dust, MOTES, wireless sensing networks, these are the name. So they are very small computers running on special operating system, like tiny operating system. That is the operating system on which these MOTES are working. They will be linked by radio transceivers and sensors to form small autonomous modes. MOTE is a generic sensor node platform. That's what I was saying. It's a generic name, which is what it is integrating: sensing, computation, and communication. These are the three things: sensing, computation, and communication. These three activities it will integrate. So this smart dust, or it is also sometimes called a magic dust, because the aim was to make a sensor of the dust size. And that is the name. That is why the name came Smart Dust. Dust particle size you should have. So University of California, Berkeley has this project which is Smart Dust. The goal of the Smart Dust project is to build a self-contained millimeter scale sensing and communication platform for a massively distributed sensor network. The device will be around the size of a grain of sand and will contain sensors, computational ability, bidirectional wireless communication, and a power supply, while being inexpensive enough to deploy by thousands and hundreds. So this is what a Smart Dust is. Inside MOTE, see, you can have only this size, 2 millimeter into 2.5 millimeter. It has a RISC processor, memory 3K, 8-bit on-chip ADC, frequency shift keying radio transmitter, memory system, communication protocol accelerators, register windows, and much more. Only in this small size you have in a MOTE. So you can have in MOTE you can have sensors for various things, like temperature could be there, radiations could be there, sound, position, acceleration, vibration, stress, weight, force. Any number of sensors you can put in that MOTE depending upon your application. And then you have to put a battery, you have to put an antenna. So sensor you have to put, then antenna, then battery. Then radio transmission is most widely used. You can use an ISM band, which is industrial, scientific, or medical bands. And the most common radio link allows a MOTE to transmit at a distance of something like 10 to 200 feet, or you can say 3 to 61 meters. sorry, this is spelling mistake, this is Dust Network. This is the company that was created to commercialize this technology. Then you have everywhere, if you go to buy in internet, if you put Crossbow modes, Crossbow provides these modes. So you can find out these modes which Crossbow provides. So here you will, that the maximum power is consumed there. So what we do is that you don't need all the nodes. So you will see what is the optimum number of nodes. You can put some of the nodes into sleeping mode. Only some you put in active mode. Then how many can sleep, how many can be active. So that optimization also has to be done. And they are using like these batteries of lithium ion batteries which have life of 2 to 5 years. Then you have D-type lithium ion batteries which have a battery life of 7 to 10 years. Then you have nickel metal hydride rechargeable batteries also. So all these you can use. Then wireless network protocol implemented in firmware. Then 16-bit A2D resolution is there. That much is there. And transmission range of 1/3 mile line of sight. That has to be there. DARPA is the agency in USA, and DARPA were the first agency which used them in monitoring the battlefield's conditions. The modes were used by DARPA for monitoring the battlefield conditions, which is a Defense Advanced Research Projects agencies. This is, you can compare the tip of the ball pen, and this is the mode size. That small is the mode size. Then there are many applications, like they will act as a microclimate monitoring systems. You can have intelligent irrigations built, like they are continuously monitoring the weather conditions, soil moisture, radiations coming, the temperatures, humidity, and then they will decide how much to irrigate, how much water to let in. So they can act as a agents for intelligent irrigation systems. So they are saying that, as I've written here also, tracking of microclimates. Then buildings, intelligent buildings could be there. You can test that it's a big building, in any apartment you can put it, or in a building where many offices are there. So there the distances will not be much. Different floors are occupied by different companies, and you can monitor that which one is using more power. You can locate it down to that line. For each line you can put these current meters, power meters. So these intelligent buildings could be there around this. So a building manager could attach modes to every electrical wire throughout an office building. These modes would have an induction sensors to detect power consumption on that individual wire and let the building manager see power consumption down to the individual outlet. So if the power consumption in the building seems high, the building manager can track it to an individual tenant. Then suppose firefighting, you have to do it. So you can spread lot of modes on that area. They will tell you how the fire is getting spread. So then it will help firefighters to curb the situation. So you can think of numerous applications. On highways you can put it, on bridges you can put it, on railway tracks you can put it. The research areas in winds. What are the actually things which are happening in winds? The most important is this energy part. This is the critical bottleneck there only, because you want, in fact I have seen that in zebras and other, like you want to monitor the behavior of the animals. Around zebra they will put one collet kind of thing in which modes will be there. So otherwise it is difficult now how to keep on taking photographs throughout the year, how they are doing, how they are behaving. Now you don't have to do anything, you have put modes and then you can keep on monitoring their behavior all the time. So habitat monitoring, these things are very popular with winds. So energy is a paramount concern in wireless sensor network that need to operate for a long time on battery power, and sensor nodes are expected to be battery equipped and deployed in a variety of terrains. Habitat monitoring also will require continuous operation for months, years, and for monitoring civil structures like bridges, they will require an operational lifetime of several years, maybe 100 years you require to deploy. So their energy becomes very, very important. And major energy consumer is radio communication. That is a major energy consumer. Now you see the comparison. 3000 instructions can be executed for the same cost as transmission of 1 bit over 100 meter. That is a comparison between processing and communication. That's the thing. So recent research, what they have found is that you can significantly save energy by dynamic management of node duty cycles. So what do you mean by duty cycles? Only this is that you make some nodes to sleep. Like we have power saving mode. Now when you are not using them, put them into a sleep mode. That will help a lot. So actually the fundamental problem is you have to maintain sensing coverage and network connectivity with least number of active nodes. Maintain the coverage and also the connectivity, but how many you need, active nodes you need, that is the real problem. So a fundamental problem is to minimize the number of nodes that remain active while still achieving acceptable quality of service for applications. Nowadays, like you have low power processors, because you have to go, everything you have to make low power. So processors, what you do is you make them run on a reduced clock cycle. So reduced clock cycle will take less energy also. Where it is not time critical things, you put them on this reduced cycling. That is called this scaling, this frequency scaling. So low power processors uses frequency scaling, where the clock frequency driving the system changes according to the system performance and requirements. It will slow down the system, but it will save the power. So if you don't want very fast computation, better go in frequency scaling. Then the battery aware task scheduling. So the scheduler will take care that it has to take care of that you have to prolong the life of the battery. So you have to selectively keep on making some nodes active, some mode go on sleep, so that you can have maximum with that same network that you have connected, it can operate for longer time. This is a very important area that has come now in modes, that is energy harvesting. What you do is you harvest the energy from your surroundings only, like solar energy. You have nowadays you have the calculators you are using, you are replacing them after so many years, you know, solar energy they are charging. Then the vibration energy, like your environment where you are. You must be seeing that so many things a person does while walking. So you are spending energy, you are moving your hands, actually the energy is getting spent. So all these energies you can utilize. So from environment you charge the batteries. It can be vibrational energy, water is flowing, wind is flowing. So all those energies you trap. And the most important nowadays coming is this piezoelectricity, strain. Wherever the vibration is there, you convert that into electricity. That vibration, that is pressure, electricity, so you convert it. So this is an active area of research in winds, which is energy harvesting. From your surroundings, you charge the batteries. So solar energy, vibration energy, wind water flow, thermoelectrical generation, that is Seebeck effect, and the mechanical strain. So strain energy is stored by rectifying piezoelectric fiber output into a capacitor bank. And when the capacitor voltage reaches a preset threshold, then power is transferred to the sensor. Then data aggregation is also another research field. So in this data aggregation means you have to decide, see when will you transmit, when will you process, that's the meaning. So data processing locally and sending only the results increases the energy used by the processor and decreases the energy of the data transmission. I mean, you process the data locally and send only the results. So what will happen? You are decreasing the transmission energy, but you are increasing the energy that is required for processing. But we have seen that energy required for processing is much less as compared to energy required for transmission. But then you should know that important data also has to be given. Then you see that is a concept of this multi-sensor fusion. Sensors are giving you outputs, then you decide that which information is important. And there will be redundancy also. No? Maybe most of the sensors are giving the same output, so why should you transmit all that? So this is an important concept, which is a data aggregation. So data aggregation and fusion plays a very important role in energy saving. Correlations in data are exploited. You see that if the data are same, then there is no need of transmitting them to gateway. So you see the correlations of the data and then do it. I think last comes the intelligent control. The intelligent control techniques, as we know, they are becoming very important these days, and they are covering areas like neural networks, fuzzy logic, expert systems, then genetic algorithms, hybrid techniques, isn't it? Machine vision. These are some of the fields which are there, robotics, which come under intelligent control. So areas in intelligent control are neural networks, fuzzy system, expert systems, genetic algorithm, multi-sensor fusion, robotics, machine vision, and then of course hybrids also. You have expert systems which are AN based, expert systems which are fuzzy based, then you have neuro-fuzzy kind of systems, then you have neuro-fuzzy combined with genetic also. So that hybridization is also there. So what are the features of intelligent control? They learn from past experience. As like we human beings also, we should be learning from the past experience. That is why we say it's a intelligent human species is intelligent, because we learn from past experiences. Emulation of human expert and brain, identifying threatening changes such as failures and reacting appropriately, robustness, self-diagnosis and repair, and integrating sensor information. These are some of the features of intelligent control. Then what is artificial intelligence? It is a science of enabling computer system to learn, reason and make judgment. To learn, reason and make judgment. So you deploy machines which mimic human behavior. Now there are many fields here, like in some fields like artificial neural networks, they emulate your brain, how your human brain works. Fuzzy logic, they emulate human decision making, isn't it? So different areas emulate different capabilities. So the AI is actually dealing with systems like features like learn new concepts and tasks, reason and draw useful conclusion about the world around us, understand the natural language processing, like the way we are speaking, it should be able to understand our language. That is important. And perform other type of feats that require human type of intelligence, like making joke. You don't expect machines to make very good jokes. Human beings are very good in making, they have the wit and humor that they have. And think of jugalbandis. We can't think of computers doing jugalbandis. If you have heard any jugalbandi program, you will be marveled that how the human beings, they are so creative, isn't it? So there are few things we cannot just expect also computers to do. So it is functionally different from conventional programming. It is more symbolic than numeric process, employing heuristic or rule of thumb procedures. Many of the AI techniques, they use heuristic, which is based upon our experience, which is rule of thumb that they are using. AI areas are expert systems. Expert systems capture the behavior and skill of experts. That is why the name is expert systems. They are based on human expertise. Like there is a legal expert system. So you have any problem, any person has any problem, any legal issues, go to that legal expert system. You have seen if you go to any lawyer, they will have whole their room will be filled with their case books only. There's big volumes are there. Now everything, then you have expert system based on case basis. You go with the case to an expert system, so all the history will come that these are the legalities involved, these are the solutions. Then you have actually the first expert systems, they came in medical field only. You have expert systems for even coma patients, for dialysis you have, for infections you have, name it, for all ailments you have expert systems. So they are kind of replacing the expert doctors. Then you have expert system for education purpose. You want to teach maths. So you have those programs which can teach maths in an interactive way, any subject. Then comes robotics. Robotics all of you are very familiar with, that you will like a robot in fact to work just like a human being only. But how difficult it is. Even things like walking is so natural for all of us. But to make robot walk like human is such a big task, isn't it? So the things which are so natural to us, in fact, then we say that children can walk more properly. So it hasn't even attained that kind of adulthood also, that it can even walk properly. But there are areas in which, like Deep Blue, it has beaten the world champions in chess. So they are very good in few things. So that is what I have to know. Then there is a machine vision and learning. So we want like on super highways, your metros are going, we want them to be driverless. We want planes to be without pilots. So they should have all this vision kind of capability. They should be able to see the obstacles and steer accordingly. So machine vision is very, very important. So what they do is that we can say that AI powered technologies have made possible such astounding achievements as vehicles that are able to safely steer themselves along our superhighways and computers that can recognize and interpret even facial expressions. You have seen the news comes now, this is the first time so many kilometers machine without any driver could go around this much kilometer in this much crowded area with that much traffic. These kind of things keep coming in news. So that they will involve this machine vision and learning. Then neural networks, they simulate our brain. Like our brain, there are millions of neurons which are there in our brain, and there are massive interconnection is there between them. That is why even if you have seen a person in your childhood and then you see it even after 40 years, you will say this person seems, I have seen this person. But you can't expect computers to do this kind of thing. It's only like our brain has such massive parallelism, correlations, that it will be able to recognize a face even after so many years. And the important concept in ANN is training. You can train the neural networks. Just like we train human beings, you can train the neural networks. So you have a set of input output data. Suppose I want to train it for y equal to x square. So I will give some inputs and I know the output. You keep on telling this network for this input, this output, for this input, for this output. Keep on telling the network and then it will learn that function. So you have trained it, say, from x equal to 1 to 10. Say 1, 2, 3, 4 up to 10. Now even if you ask what is the square of 1.5, it will give you the right value. Or even if you ask the square of 12, it will, though you did not train it for 12, but it has learned that pattern, then it will give you that value. So this training is a very important concept of neural networks. Then you have fuzzy logic, and this person, this Professor Jadeja, is the, you can say, the father of this fuzzy logic, and he's a professor in Graduate School Computer Science Division in Department of Electrical Engineering and Computer Sciences, and he's also director of Berkeley Initiative in Soft Computing. So his thing was that we don't need so much precision in the word in our day-to-day activities, and if we employed this, that our tolerance for imprecision, that is what fuzzy is. Like normally we have vague concepts, there is an ambiguity in our description, and we are able to work well with it. Like you have a driving instructor. Driving instructor says that suppose you see a red light, so immediately apply the brake. But suppose driving says that if you see the red light at say 5 feet, apply brake at this rate, you will not be able to understand that. But if he is speaking that language, you can understand it. So this impreciseness in our language, that is very well understood by all of us. So this fuzzy logic is exploiting that vagueness. So it works with uncertain and partial truths to obtain crisp result. But in contrast to ANN, you need some knowledge of the system, because you will say some rules will be, you will be framing that if temperature is high, pressure is low, do this. If it is very high, if it is low, then what you do it. So that way you should know the system, then only you can frame those rules. So ultimate aim is to make computers think like human beings. So this is, Jadeja had said that most applications exploit its tolerance for imprecision. Because precision is costly, it makes sense to minimize the precision needed to perform a task. So you should know that where are the applications, which applications can tolerate imprecision. Of course, when you have to shoot a missile, you have to launch an aircraft, there you cannot have fuzzy kind of things. There precision is very, very important. You have to make microchips. So there you have, precision is the most important thing. So there you will not apply fuzzy logic. But our day-to-day things in industry, you have to work, you have to control. How does it matter? Level is 5 meter or 5.1. It doesn't make much difference. There you can go for that. So the ultimate aim of fuzzy logic is to make computers think like human beings. And these are the three lures. What are that? Common sense, human thinking and judgment, which are the lures of fuzzy logic. Now this is again a quote of Einstein, that as far as laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. Yeah. So genetic algorithms, they are based upon, like we say, evolution is there. Continuously we are seeing, when we see our youngsters, our small children in our houses, we always make a comment, they are very intelligent, they are very sharp. Because generations are evolving, it's an evolution process. So here also genetic algorithm use that only, it evolves, it optimizes the processes. So it's based on that biological processes only, the fittest will survive and the best and best solutions will be taken. So I think now I will conclude that about this artificial intelligence part. Isaac Asimov is a very famous science fiction writer, and he said that I think it is important not to worry about whether computers will replace us, but whether we can make computers even better at what they do, so that together, cooperatively, we can proceed much faster and much more effectively in elucidating the secrets of universe than either type of intelligence can possibly do alone. There is always a debate now, machine intelligence versus human intelligence. People are scared. You have movies like Matrix you have seen. Their machines are becoming so powerful. So they in fact sort of overtake the human civilization itself. So these kind of things are, like they say that robots also, you have seen artificial intelligence movie only, in which that robot has so much human emotions. He can love his mother, he cries, they have consciousness. So these kind of things are being projected by, you can say, science fiction writers. So that is what Isaac Asimov said, that more important is, it is not that they will replace us, but we should work together in cooperative way. That is more important. And actually the thing is that real danger is not that computers will begin to think like men, but that men will begin to think like a computer. That is actually the real danger. And actually it is so happening now. You can see the mechanical systems, we want them to be more and more biological based. We want human beings, these robots, to look like just humanoid. They should look like human beings. But human beings are becoming like robots only. So natural things are becoming mechanical, and mechanical things you want to be more natural only. So that is the irony in fact. So thank you.